Hello, everyone. Welcome back. So at this point, we have observed um, the various complex functions and their calculus behind them, right? So I'm going to talk about um, the exponential and logarithmic functions in detail because this is where complex variables become pretty crazy. Okay. It'll become even crazier when we look at zeros of complex functions. So stay tuned for that. But for now, let's look at what the exponential function is first in the context of complex variables. Okay. So we looked at the exponential function in previous videos. So let me write that out again. So if z is equal to x plus iy, right, then the complex exponential e to the z, this equals to e to the x plus iy. And then in terms of the real and imaginary components, this equals to e to the x times cosine y plus I times e to the x times sine y. Right? That's the definition of the exponential function. Okay. So the real part is e to the x cosine y, and then v is equal to e to the x sine y. Okay. Um, let's see. And let's go over first the derivative of this function e to the z, right? As you would expect, the derivative of e to the z is just itself. Okay. And the idea behind this, so the proof behind this, okay, so the proof behind this is, well, we want to show that e to the z is analytic, right? Uh, just, and that's just using the components u and v and showing the Cauchy-Riemann equations are true, right? So the partial of u with respect to v in this case, a partial of u with respect to x, not v, this would equal to e to the x cosine y. We treat y as constants, and the derivative e to the x is just itself, right? Partial of u with respect to y, this would equal to minus e to the x sine y. We treat x as constants, and we differentiate y, okay? Likewise, the partial v with respect to x, v is e to the x sine y. Well, that's just e to the x sine y, right? Partial of v with respect to y, this would equal to e to the x cosine y. All right. Well, for one thing, these are equal. These are equal, right? Partial of v with respect to x is equal to the partial of v with respect to y. That was the first equations in the Cauchy-Riemann equations. The second is the partial of u with respect to y is it does equal to minus partial of v with respect to x. So minus partial of v with respect to x. So they do satisfy. Okay, so we know that e to the z is analytic, right? E to the z is analytic. All right. Um, so okay, so we know that e to the z is analytic. And we know that f prime of z exists. And take note of this. This was in so by 3.2 in section 3.2 in the textbook. f prime of z, this equals to the partial of u with respect to x plus I times the partial of v with respect to x, right? So this is one way of showing what f prime of z equals to. So f prime of z is the partial of u with respect to x, which is e to the x cosine y, plus I times the partial of v with respect to x, which is plus I times e to the x sine y. Okay, this here's the definition of e to the z. Okay, so f prime of z equals to the partial derivative with respect to z of e to the z. Let's just say e to the z is itself. Okay, is itself. So pretty cool, right? So that's one of the first things to notice is that the derivative of e to the z is just e to the z, what you would expect. Okay. So for example, I want you to try to find this derivative. Figure out the derivative of that function. F of z equals to e to the z squared minus 1 plus I times z plus 3. Okay, so pause the video and I want you to think about this for a bit. Okay. All right, this should take little time or no time at all, but really f prime of z is just, so you're going to use the chain rule here, right? So f prime of z is just, well, e to the z squared minus 1 plus iz plus 3, okay, times the derivative of the inside function, which in this case is the exponent number, which is 2z minus 1 plus I. Okay. That's just the derivative f of z. Okay. All right. So good review for derivatives, right? So next, I want to talk about the modulus, the conjugate. And the argument. Of e to the z, okay? So w is e to the z. Then, so we can express w as e to the x cosine y plus I times e to the x sine y, right? In terms of the horizontal and vertical components. Okay, for any complex number, we can express it in terms of the polar coordinates. So we can express w equals to r times e to the I theta. Okay, e to the I theta. So what this means is that, okay, so r times e to the I theta, this would equal to e to the x times e to the I y. Okay, let me write it like this. Since these numbers are equal, what that means is that the radius has to equal. So r has to equal to e to the x. Okay. And theta is equals to y. Let's stop here, right? But not only theta has to equal y, all right, so by definition of the exponential function, we are dealing with two periodic functions, cosine and then sine of y. So if I have an angle y here, right? If I rotate that angle 2 pi radians clockwise or counterclockwise, counterclockwise or clockwise by 2 pi radians, or any multiple 2 pi radians, you would get the same result. So theta could actually equal to y plus 2n pi, and that's it, right? So let me write this in the same color. 2n pi for n is 0, plus or minus 1, plus or minus 2, any integer, right? So n is a integer, and if we multiply, if we add y by a multiple of 2 pi, we would get the same result for cosine of y and then sine of y. Okay. So and then theta would represent the argument of, so theta would be just the argument of w, right? In that case. All right, so that's how we would determine what the radius is and what theta is in terms of the exponential function. Okay. Yes, and then e to the x, as you know in the algebra, e to the x is never 0, right? So what we want to have as a condition is that the modulus of r is positive. Okay, absolute value of r is positive. Okay, so take note of that as well, right? So that's how you would figure out the modulus and the argument of the complex exponential function. Moving on to the conjugate, though. So the conjugate. Okay, moving on to the conjugate. So if I want to take e to the z conjugate, well, by definition, this is just e to the x cosine y minus I times e to the x sine y. Okay. Another way to write this is just e to the x times cosine of minus y plus I times e to the x times sine of minus y, right? Okay. So this equals to e to the x times e to the minus iy. But this equals to e to the x minus iy. Right, so if I have z equals to x plus iy, then e to the z conjugate, this equals to e to the z conjugate. It's just conjugate the, take the complex conjugate of z and then just apply the exponential function to it. So essentially, e to the z conjugate equals to e to the exponent number z bar. Okay. So let me real quick list out the properties of exponents of the exponential function. So z1 and z2 are complex numbers. Okay. E to the 0, that is 0 plus 0i. This will equal to 1 plus 0i. So e to the 0 is 1. Okay, that's true. E to the z1 times e to the z2. This equals to e raised to the z1 plus z2. Okay. Third condition, e to the z1 divided by e raised to the z2 equals to e to the z1 minus z2. Okay. And then part D is this property. These are pretty straightforward to prove. It just takes a lot of algebra to work with, right? And then the fourth property is if we have e to the z1 raised to the n, that equals to e to the n times z1. And since we have cosine and sine as part of the definition of the exponential function, n is a positive integer. So it has to do with the periodicity of those functions, right? That's why n is just any integer. Okay. So yeah, so these properties are relatively easy to show. Just let z1 equal to x1 plus iy1, and then z2 is x2 plus iy2. Okay. And then literally these right here, you're just adding the real and imaginary components. Okay. And you're just using properties of exponents you've seen in college algebra. Okay. So relatively easy to show. Okay. So the next thing I want to talk about is the periodicity of e to the z. So we're going to look at how inverse functions are formulated in the complex variables. And forming inverse functions would have to constitute showing that a function is one-to-one on a specific domain. Okay. And in the terms of complex variables, we're going to have to restrict our domain so we would have a principal definition of what an exponential means and what a logarithm means. Okay. So real quick, let's go over the periodicity of e to the z. So we know that e to the z is e to the x cosine y plus I times sine e to the x times sine y, right? E to the x sine y. Okay. And we know that theta is equal to y plus 2n pi, right? N is some integer, okay? This letter right here, this corresponds to the set of integers. Okay. So it's just -2, -1, 0, 1, 2, and so on, right? It corresponds to the set of integers. Okay, so what I'm saying here is that theta can equal to y plus 2n pi, for which n is an integer. Okay, n is equal to an integer. Okay, so since cosine and sine are periodic, right? If we have theta equals to this quantity, we would get the same value, right? So really, this this quantity down here, this would equal to, well, e to the x times cosine of y plus 2n pi, right? Plus I times e to the x times sine of y plus 2n pi as well, right? And so this would equal to e to the x plus I times y plus 2n pi, right? Which is just e to the z plus I times 2n pi. Okay. So these values would be the same. These would be equal. Okay. And also when n equals 1, we'll get the period. we'll get just one period of that function, right? So therefore, e to the z would equal to e to the z plus I times 2 pi. Okay, I times 2 pi, excuse me. So since we have a periodic function, what we need to do now is we need to create a region where the exponential function is well defined. Okay. In other words, we want to figure out a restriction for our domain for the exponential function where it's 1-to-1. Therefore, we can construct an inverse for that function. Okay. Because one of the conditions of a inverse function is that 1-to-1 implies an inverse exists. So that's important. Okay, so we're going to have to construct what is called the fundamental region for w equals e to the z. Okay, and so the fundamental region would be this. So if you notice, e to the x, this is never 0, right? So the domain in terms of the real numbers is all real numbers, right? All real numbers. So we can actually say, so if you look up here, right, e to the x, we would get a, so it's 1-to-1 on the real numbers. So its domain would be the entire real line. Okay. And then for y, this is where we'll have our fundamental region. So we want to reflect the limits on y in terms of the principal argument, right, of a complex number. So the restriction for y here is that y is in between minus pi and then pi. And it's including pi. All right. So the fundamental region in the complex plane would be just an infinite strip. Okay, so this would be an infinite strip. So minus pi would be here. And then pi would be so here. And so this right here would be the infinite strip that we want. Okay. So this is the infinite strip. And that's what we want here. Okay. Right. And so if I were to pick like different values for z here in this strip, okay, we would get the same exact value if we increase by 2 pi. So if I add 2 pi here, I can still get the same value for z here, right? So that's why we construct this fundamental region. Okay, so this here is the fundamental region for the exponential function. Okay. And also, let's talk about their mappings. So let's look at a map. The mapping of the exponential function, e to the z. All right, so we're going to concern with the fundamental region. Okay, so, oh, geez. This is the complex plane. Okay, so we're going to look at some various curves in the z-plane. And we're going to look at what those look like in terms of the w-plane. Oh, Jesus. All right. Okay, so let's look at what vertical lines look like. So if I look at, say, this line, right? So say, let's start off x equals 0. Yeah. And I'll do x equals 1. Okay. And I'll do x equals minus 1. So if x is 0, what that means is, well, so that means the y is varied and the x is fixed at 0. So that means u is e to the 0 cosine y, and then the v coordinate is e to the 0 sine y. In terms of the real numbers, e to the 0 is 1. So we'll just get cosine y, and then we'll get sine y here. Okay? So in the w plane, this will correspond to cosine y plus I sine y. That's just the unit circle, right? Y is in between minus pi and pi. So this will correspond to the unit circle. Okay. So this is where x is 1. Okay. So this will correspond to a circle. Okay. And also like when x is 1, we'll just have u is equal to e times cosine y, and then v is equal to, so x is 0 here, e sine y, right? Okay. I'll just do x is equal to 1, so we'll get a better idea what this image is. So w in this case is e times cosine y plus I sine y. This will correspond to a circle of radius e. So much bigger circle, right? So the modulus here is e. Okay. And if you have negative values, you're just going to have a circle with a smaller radius. So try looking at x equals -1 on your own. Okay. So with vertical lines, x equals k, they will get mapped to circles where the modulus of w equals e to the k. All right. This is going to be a long section. I may do a two-part. I might do 2 parts for this section. Yeah, this section is quite long. So let's see. But anyway, I'll just drive on. So what about horizontal lines? We looked at vertical lines. How about horizontal lines? Okay. So going back to this fundamental strip here. Okay, so the fundamental strip should be right here. Okay. And then here is the W plane. W plane. And then so okay, so we're gonna look at horizontal lines. So let's look at for example, what y equals pi over 4 looks like. Y equals pi over 4. So that means your x is varied, right? So e to the x times cosine of pi over 4. And then the v component is e to the x sine of pi over 4. And so these would imply that it's just e to the x times root 2 over 2. And then v is equal to e to the x times root 2 over 2. So the complex value w, this would equal to e to the x times root 2 over 2 plus root 2 over 2 times I. Okay, so what this implies is that w, so for w, this would be just a positive ray that's shooting out in the direction of the argument of z, the argument of this complex number, I should say. So the argument here is just pi over 4. So what we'll have here is just a ray that is shooting off in the positive direction in the first quadrant. So this is where the argument of z is pi over 4, right? Okay, so okay. And then and if I were to look at, let's say, another line, let's say y equals minus pi over 6. Okay, so minus pi over 6. Okay, so that means the u is just e to the x times cosine of minus pi over 6. And then v is e to the x sine minus pi over 6. So that means the w coordinate is equal to e to the x times root 3 over 2 minus minus 1/2, right? So okay, so really we're going to have an array that that is spitting out in this direction, right? Spitting out in that direction. Okay. This is where the argument of z is minus pi over 6. Okay. minus pi over 6. Okay, so really, horizontal lines y equals k. Get mapped to lines where the argument of z is k. All right. So, okay. And there was one more. So, was there one more? Let's see. Yes. Okay. Um, oh, and one more thing. And another thing is that the mapping. So the points where x is varied, they get mapped where the modulus of w is positive. Okay, that's the other important thing I want to mention too. So yeah, make sure that the modulus of the radii is positive. So this is going to be a two-part series. There is a lot in this section. So so in the next video, so we looked at the complex exponential function, and I will go over the complex logarithm function in the next video. So stay tuned. Thanks for watching.